If we start with two independent variables, x, which is a standard normal, and z, a chi-squared with n degrees of freedom. They're independent, so writing down their joint density is easy. I just write down the product of the two densities. That's just writing down the two definitions. Now, at this point, you all look like trusting people, so we'll just go on a bit of what may seem like a strange journey. Just as we did deriving the density of a chi-squared, where I started by saying, I wonder what the distribution of the square of a standard normal is. Here I'm going to say, I wonder what the distribution of x divided by the square root of z over n is. So I'm wondering what the distribution of a standard normal divided by the square root of a chi-squared normalized by its own degrees of freedom is. Now I'm going to do this multidimensionally, so I'm doing the change of variables y equals z, which you may think is a little bit redundant. It's no more than renaming it, but it at least tells me that I've got a sense check on the distribution of y, which should also be chi-squared with n degrees of freedom. But if I do that change of variables, I don't want the x and the z, I want the y and the t. So if I set those up, then I need my Jacobian associated with that change of variables. And my Jacobian here is the square root of y over n, or the square root of y over n. So when I now substitute through my change of variables, replacing x with t times the square root of y over n, and replacing z with y, then I will get to that by the time I've multiplied by the square root of y over n, which is the absolute value of the determinant of the Jacobian. Now when I tidy that up a bit, I get to this. Don't worry if you're slightly put off by this. I won't ask you ever to write any of this out. But simplifying further, I get to this point. Now, this is not something nice and simple, because I've got the t's and the y's tangled up with each other, because they're not independent of each other. So unlike when I derived the distribution of a chi-squared with n plus n degrees of freedom, maybe a video or two back, we could see the separation and we could just pull the two distributions apart and say they're independent. This distribution is this distribution is something else. This is not quite as easy as that. I'm going to need to integrate out the y to get rid of that from the joint density function, to get the marginal distribution of t, when all I care about is t. So I need to integrate out over y. Now y, I know, is a chi-squared variable, so only takes non-negative values. So I need to integrate out over 0 to infinity. Well, the first thing I can do, I can pull all of the terms that don't depend on y out the front. And in fact, in this case, they're all constants. Now, this is not easy. I need another change of variable in there. So rather than doing my integral with respect to y, I'm going to do the integral with respect to v, where v is y over 2 times 1 plus t squared over n. Again, don't be too put off by the details of this. But this is getting me towards the marginal density of t. With this, admittedly, not easy to spot change of variable, what we're left with at the back is an integral which we can evaluate through comparison to the gamma function. We saw that in a previous video where we introduced the gamma distribution, and it was this interpolation between the integer values of a factorial function, a kind of generalization of factorials for non-integer values. So with this recognition that in fact what I've got there is the gamma function evaluated when alpha minus 1 equals n plus 1 over 2 minus 1, then it'll evaluate to a gamma function. So I just tidy that up a little bit. I say tidy, it's not particularly tidy even now. But what I get there is I get the marginal density, or the distribution of t. As ugly as this looks, it is a standard distribution, a t distribution, or sometimes called a student's t distribution, with n degrees of freedom. Because if you remember, it relied on a chi-squared with n degrees of freedom, so the same n. And this is the greatest piece of mathematics or statistics ever invented for the love of beer. It was developed at the Guinness Brewery in Dublin by William Seeley Gossett, who was a statistician looking at quality control issues in the beer. I'm not sure why, but he didn't publish his work under the name William Seeley Gossett. Instead, he wrote that this was written by a student, or the student. Not sure why. So a t distribution is just a standard normal divided by the square root of a chi-squared n divided by n. And that is the somewhat eccentric man who liked to control the quality of beer. So what does this distribution look like? Well, symmetrical about 0, it's got expectation 0. And it's going to look a lot like a normal distribution, because if I had a normal distribution divided by a constant, it would still be a normal distribution. Here, I haven't got that, but I've got the unknown variation in the chi-squared in the denominator, or the square root of the chi-squared in the denominator. And what I get to is I get to something that's sort of like a bell curve, but heavier in the tails. So if I look at a chi-squared with 1 degree of freedom, the red, looks a bit like a bell curve, but it's a bit lower in the middle, and it's got a lot more tolerance of results quite a long way away from the center. So it's got heavier tails. As the degrees of freedom increase, I get more and more certainty that the distribution, that the observations from this distribution will be close to that expectation. So it sort of fattens up in the middle and the tails thin out. It becomes much more like a standard normal. And in fact, once you get to a large number of degrees of freedom, they are basically imperceptibly different from each other, the t and the standard normal. Again, different textbooks might give different thresholds, but once you get beyond about 30 degrees of freedom, there's very little point in considering a t distribution, because you can say it's effectively a standard normal. But for small degrees of freedom, you can think of it like a standard normal, but adjusting for the fact that you might have observations a bit further away from the mean coming up more frequently. I won't go into it here, but we will see the t distribution again later when we revisit the fundamentals of linear regression. And the reason for that is if I've got a standard straight line linear regression model, y is alpha plus beta x plus residual error, epsilon, intercept alpha, slope term beta. If I don't know what the variance of those residual errors is, and I have to estimate it from a sample variance, I'm estimating it from effectively a sum of squared normals. so I'm estimating it from something which is chi-squared. So by the time I need to divide by the square root of the variance, I'm effectively dividing by the square root of a chi-squared. So I get to this t statistic in those cases.